what does the word tight mean when it comes to muscles? When it comes to the calf muscle, specifically in this case? Because we say that a lot. Hamstrings, for sure. Certainly our quadriceps get mentioned when it comes to tight. But what do we really mean? Oftentimes, we imply, or it implies to us, that the muscle is short and unmoving. And this could be the case, for sure, but it's not often discovered as to what the exact issue is. And this is something we should definitely go for. We're often looking just to release it by magical positioning or rubbing the exact right spot. And, it doesn't really make a lot of sense because there is not a clear understanding of what caused it. That ambiguity or lack of knowledge tends to lead us down the wrong road. So we have to really figure out what the real problem is. When we have a tight muscle, we've got to figure out what the cause is. One of our followers asked us about this. What's the cause of a tight muscle in the calf specifically? And this got us thinking about really the whole understanding of the concept that needed much better clarification. And so oftentimes what people are asking about is, why can't I dorsiflex? That would be this direction. The opposite of that, plantar flexion, where the toes actually go down, so that direction, and then the heel would technically come up. That would be plantar flexion. But most of the time, it is dorsiflexion, the inability to do this, that we call a tight calf muscle. And again, there's more than just the muscle involved. There's more to it than the muscle just being short. In fact, the muscle could be too long and resisting it, just coming from a different source. It implies a problem with the muscle, the fact that we can't say dorsiflex. It implies that the muscle is related to the problem, but it doesn't mean it is just the muscle. And in fact, over time, really nothing can be just one muscle. So we're going to give 4 possibilities, 4 maybes, of what could really be the problem with this ankle/foot problem. 1 is an anterior talus. 2 will be a higher nerve compensation. 3, fascia stretch. And 4 is a protective contraction. So let's get going. Let's start with that first one. Start with number 1, the anterior talus. Now the talus, do understand, is this bone here. It interfaces with the tibia and fibula, these 2 guys, one on either side. And from the front it looks kind of like this. There's, say, the tibia, and there's the fibula. This is your standard mortise joint, and the talus interfaces like that. Of course, there's fluid in between. It's a synovial joint. Of course, there's cartilage, so it's got some clearance. But we do have 2 interfacing surfaces. 2 surfaces, 3 really, but definitely 2 major ones that need to move. So when we're going from dorsiflexion to plantar flexion, or the other way around, we're doing this type of a motion. The foot is pointing its toes down, pointing them up, and that talus is gliding on that fib area. And in fact, goes back and forth a little bit as it does that. It's not a perfect pin. No joint actually moves like it's proposed mechanically. These are just representations. So when it's going into plantar flexion, it tends to move forward. And when it's going into dorsiflexion, it tends to need to move backwards. This is a clearance issue. And so we expect those things to happen if we want good dorsiflexion. And this is great when it's working well. However, there are some situations, let me get rid of a few of these things, some situations where we can actually get it so that talus comes anterior, it comes further forward than it should. So it moves just a little bit. So I'll just move it slightly forward like that. And we're talking, maybe a few millimeters, a very, very short distance. But the problem with that is, as it gets driven forward, these 2 surfaces, what will be a flat surface here, let me just do that properly, will be a relatively flat surface here against that rounded surface, are not clearing each other effectively. In fact, when it tries to go into dorsiflexion, this talus will press up against that flat tib-fib surface. Again, mainly the tibia, but it'll press up earlier than it should. It won't effectively come backwards anymore, so it essentially bottoms out the joint earlier. So the tailless, really the whole foot being forward, is essentially what is causing this. And so it doesn't have necessarily anything to do with this gastroc muscle, which is all the way over here, and will certainly pull into plantar flexion. It could be involved in keeping it there once it gets there, but it's not going to prevent dorsiflexion with an active contraction, and that's a big difference. It doesn't mean the nerve tone is wrong, doesn't mean that the muscle has been horrifically strained, so we can't blame those calf muscles for this case. Now, one possibility, one we think reasonable possibility, just more as an explanation than anything, is an improper or too hard a heel strike. So when we're walking, legs swinging through like that, and at one point the foot has to come down to the ground to meet the floor, and there is a heel strike, an impact point, where it goes bang on it. It shouldn't do it too hard. But if it were, for instance, the fact that the leg is actually coming down at this exact moment, it's going this way to hit the ground, and the heel, if hit too hard, too suddenly, too dramatically, is essentially being pushed forward. It's actually staying in place, whereas the tib-fib is going backwards. The contrast there is important because the weight of the body is now coming through this whole leg leverage system. The weight of the body is now pressing down like that. But the heel, having struck too hard, being, instead of rolling, is doing an impact point. It's hitting right here. So that stays in place. It's essentially fixed in place, and it translates the true leg, tib-fib, backwards on it. And it ends up that the tailless on the tibia-fibula articulation is pushed forward. Now, this would take a lot of time. Eventually it would have to be that the tissues between the joint capsule here and the ligaments would have to shorten up to accommodate. And so that means it's a developmental process. Now, this is a theory simply to explain a point. There are other possibilities. For instance, the anterior muscles of that tibia could shorten up as well. They could, tailless anterior, for instance, some of the, well, there's only two major top of the foot muscles, but those could shorten up as well and end up, we result with an anterior tailless that is being held there fascially, myofascially, in fact. So these are just possibilities. There are other mechanisms. Twisting motions can get you the same result, but ultimately they do take a lot of time to make this happen. This is not an instantaneous process. Something that would do it rapidly would more than likely break the calcaneus first. It would break your heel bone. And so you wouldn't really be worried or questioning why your ankle's not working right, because you've just shattered your heel bone, which hurts a lot, I assume. I don't want to try. Okay, next point. Clear some of this away. So next point, let's talk about a confusion of positions. And this is something we might call a compensation. A lot of the time we'll talk about nerve irritations. And we do so often in the form of, let's say, disc herniations. And that's nerves irritated at a higher source, coming down, and maybe they go to the calf muscle. And maybe we could theorize that they stimulate some kind of a reflexive contraction. That's not unreasonable to say with that disc herniation or bulge, for instance. But the reality is, for a disc herniation or bulge to really cause any kind of a motor effect, it is very extreme. And most of the time, that's not it. Realistically, it has nothing to do with it. Most of our musculoskeletal problems are compensatory. We have a big involuntary nervous system. We have almost no control over it. And the fact is, your compensations are pretty hardwired into you. So the trick that kind of happens all the time, is we have to make the body believe that it needs to contract that calf muscle. So what's going on? Let's say, again, we want to disrupt the motion of the ankle. I mean, I don't want to, but that's what's happened. So the gastrocnemius muscle, calcaneus, and it's just above the condyles of the femur, supracondyle area. Now we could implicate the soleus too, and there's certainly nothing wrong with that. Making that triceps surae. I'm cool with that. But in any case, mainly we're talking about the gastrocs. Understand we could mean both. So they're about there. And they have as much function as any other muscle, and that they involve the whole body. And so if we could somehow make it so that something in the body moved, that the body believed it needed to send the signal to the gastroc, to the soleus to contract, accurately or inaccurately. It could be totally right in doing so, or it could be totally wrong in doing so, but the result is still there. The compensation is built into the system, and it does so. And it creates an unnecessary gastrocnemius contraction, reducing immobility. So, this is, of course, for balancing something else. And our nervous system actually is made to do this. And if you wanted to look into this at any point, there's the cerebellum that is under major controls of this. Basal ganglia is another good place to look. And of course, our favorite, the extrapyramidal tract system, shows some of this wiring in action and shows some of these important integrations. It's really neat. And basically, really basic, if one part goes anterior forward, one must go posterior. And this usually continues up the chain. Now, just as a little side note, to prove a point, but just as a little side note, the gastroc and soleus are often seen as plantar flexion muscles. They are supposed to do this when they contract. And that's totally correct. But understand that a lot of the time they are pressing on the ground, especially in standing. So if we're standing here and we're on the ground, consider what action they will have. You can't push through the ground. That's fixed. So if I contract that gastroc and soleus in this position, ultimately what would happen is that the body as a whole, or at least at first the leg, would move posterior. And because it's attached to everything above it, so would the rest of the body with it. And this seems, pointless. Who cares, at first glance. But the reality is it becomes a postural muscle in this way. Because if by chance we've got something forward, say a lumbar spine, with a sacrum attached to it, leading up to a thorax somewhere in and around here, if that has drifted forward at all of a sudden, especially if the whole body goes along with it, all of a sudden that gastroc muscle, seemingly only a plantar flexion muscle, can be in assistance of reversing this. So that calf muscle tightness, generally tightness at this point, it is contracting, is just compensating for something much higher. Really, honestly, a reasonable thing for it to do. And in fact, it does this all the time. Pay attention to yourself when you're just standing. You may notice that you lean forward onto your toes and back off, and you can feel your gastroc muscles contracting, and your soleus, of course. So this is a bigger integrated postural mechanism going all the way down to the foot. So as an example, we can create something that goes forward that might just trick the body into believing that the gastroc needs to contract. So just as an example, and you could do anything really. Let's say the innominate rotated forward. We call that like an anterior innominate. Could be an anterior pelvis in general, but let's just say it's one-sided. We got like a sagittal plane thing going on. So it is technically come forward, even though, let's say, the rest of the body is totally normally compensating around it. Nothing's going on there. Everything else is in a relatively good neutral position. The knee hasn't really changed. We're all check mark on that. But at the same time, this compensation is so hardwired into the system, the body may believe it needs to contract that gastroc regardless. We've got a really anterior innominate, a really forward motion of that joint. And so it goes, hey, we need to contract that gastroc. And you will find that if you're able to test this, you can lay a person essentially flat on a table, and you can move and change the position of certain points. Lumbar spine is a really good example, but you can go as high up as the neck if you want, and you can read the change in tension in the gastroc just by feeling alone. You can also motion test that ankle. You can change the position of the arms, the lumbar spine, and the neck, and you can get minor changes in the gastroc tension. So this is hardwired into the system. And it means that regardless of what you think should happen, it's going to do it anyways. It's going to do it involuntarily, and it's going to do it in a way that is consistent. And that's consistent over time, especially. That's the important thing. It's consistent over time, so it will stay there for a long, long period of time. You could go like right up into the skull with this stuff. Let's not get that complicated. That's a later discussion. Okay, point number 3. The fascia is stretched somehow. The fascia is stretched, but the muscle's kept in a long position with no contraction. And you may be asking, well, how could that happen? And it's actually pretty easy. Understand that the gastroc muscle is tied up in fascia just as everything else is. There are many layers of fascia on the body. Things you've heard before, I hope. I'm sure you have. And just everything is tied up in this fascial sheath. Many fascial sheaths all around it. Every single nerve, artery, vein. There's a whole fascial body, and I know it's in no way separate from the rest of the body, but just understand it can technically be separated in a way. So this will all tie together. So imagine for a second we can make it that so this back part is lengthened. We're getting a pull somehow, and we'll go into what creates that pull eventually. But the fascia is lengthened. It should not always, but should pull that gastrocnemius along with it, all of the calf muscles. It should pull it along with it because they are one and the same. You can separate it. It takes a scalpel. You can separate it. But as the fascia lengthens, so can the muscle. And in this case, the muscle has not contracted at all. However, because we have a pull being exerted on the calcaneus, going up basically in this direction, roughly this direction, it's going to make it so that it wants to plantar flex. Therefore, it is harder, even with active muscle contraction of the front muscles here, so the anterior muscles, even if they are yanking up, it can't reverse. It can't defeat this fascial pull. So it will overcome it, or at the very least, it'll make it a lot harder. And it has nothing to do with active contraction of the muscle. In fact, the muscle is essentially fine. There could be some strain going on for sure. It may result in a thickened fibrous muscle. But there are many situations in which just the fascial pull alone will make it harder to dorsiflex. So some of the things that can create that, though, because it's, again, not that simple. We got to figure out what caused that. That's the important thing. So get rid of a few of these just for our illustration purposes. We've got, again, a number of different things, and many of them will be the same. But, again, taking that anterior innominate, because all that fascia is tied up in that, because that's a transverse axis. Forgot to mention that the first time. And as we anteriorize an innominate, it pulls up like that through the hamstring fascia. But this ties in all the way through that popliteal fascia. So it's not like it's separate. Fascia spans in a way that muscles don't necessarily. And even though they're all tied together, those fascias, those long lines of fascia, can create stretch at great distances. There's some give, of course. But as we change the position of that innominate, as we anteriorize it, or the whole pelvis, you can see it happening on both sides or one side as a result of that. Another good possibility is you could actually have, it's funny how this works sometimes. You can actually have a totally posterior pelvis, but because the whole upper body has bent forward for whatever reason, now that's maybe a flexed lumbar spine, even a flexed thorax, we could still elongate all this tissue to follow that body up into that flexed position. So there are many possibilities. And again, ultimately this just pulls all the way down to the calcaneus. It's pulling in a number of spots. It could cause effects in the knee, could cause effects in the hips, but ultimately we are pulling on that calcaneus area. It's going to change the way we dorsiflex. It will resist that and limit how that works. Again, many other possibilities. All of them, ultimately, it's possible to reduce dorsiflexion. It's possible to make it feel like that calf muscle is tight. But again, until you run the structural diagnostics, till you test, until you palpate, you're not really going to figure this out. Okay, last one. And of course, as I always say, there's many possibilities, many answers we could do to make these. These are just the 4 I happen to have chosen. I think they make some sense. They're not perfect, but they're okay. All right, last one. An actual contraction, a protective contraction. And that's an important statement right there. When something is protective, you do have an idea what is happening. So the gastroc, again, is tied in. Supracondylar, calcaneus. Now you can never forget that. And let's say, now I've drawn it really far away, really far off the body, but it's not really, it doesn't really look like that. It's quite a bit closer. And so understand that when we pull on a muscle, when we actually pull on a muscle, it is being yanked on, and this is a potential damaging thing. So let's just say, as an example, the femur, for whatever reason, is forward, relatively forward, and that just could be because we've got a hip flexor response, and it's bending the knee up a bit. Could be that the tibia is in fact backwards. This is also a possibility. Again, I'm just giving you examples on a local level. And so when this is the case, it's not going to be instantaneous usually, but when this is the case, usually as we walk, as we step, because the distance between 2 points has increased. So this distance here, let me draw that a little bit better, there and there, this distance has increased, and especially when we load with weight, as we put the body's weight through and down into the foot, down into that heel, it's going to elongate that muscle a little bit further. There will be, if it's just right enough or just wrong enough, depending on how you're looking at it, it's just wrong enough to cause strain in the tissue or to cause it to lengthen beyond what it should be comfortable with. So as the length goes up and up and up, there is a point where it could tear and permanently damage the muscle. So it does exactly what it should do. And this is through the muscle spindle fiber. This is a well-known thing. When a muscle is over lengthened, what it will do is it will send a bunch of signals back to the cord, and there'll be an interaction there at some point, and will increase the tone. That's a terrible color for, there we go, green, why not? It'll increase the tone of the muscle. It will ramp up the tone of the muscle, and the muscle will be contracting in an attempt to preserve itself. It would be very foolish to do otherwise. Why would you have a muscle that didn't resist over lengthening? It's kind of a foolish design. So every single muscle has that capacity to resist that over lengthening, the potential for damage. And this is a very important function. And so again, we can look at it as not anything wrong with the calf muscle. In fact, we can look at it as everything right with the calf muscle. In fact, to take it even one step further, if we had this shortened calf muscle, and we got in there and we just started really stretching it back and forth in all kinds of different directions, and really loosen up that calf muscle as much as we possibly could, we may actually end up destabilizing the structure completely, worsening it, weakening it, or even exhausting it to the point where it can't do its basic job of self-protection, and we rupture that, maybe the Achilles, maybe we tear the gastroc further, we make it worse, in fact, by overstretching it. You'd have to do it very forcefully, but this is very much a possibility. And so you have to consider that. You have to consider, too, that, in fact, you might destabilize the structures above it, because we could be protecting the knee to some extent as well. We could be protecting the hip even. And so just ripping through that muscle, just with little concern for what it's guarding against, is a really bad idea. Systemically, it causes all kinds of extra problems to force through something. So, all that being said, again, we can go all the way up the body, because maybe we made the example of the tibia being misplaced, the femur being misplaced, the hip, but we could go as high up again as the skull, as the lumbar spine, because these are all shared functions, these are all shared movements, and that's a real important consideration to make. These are just the things you have to do when you want to figure out why something is the way it is. No thanks, Siri. Anyways, man, I hope that made sense. Because that was a one-taker.